My name is Edward, and today I'm going to talk to you about computer vision. And by the end of this talk, you're going to understand how computers turn images from pixels into a more meaningful embedding format, which can then be used to classify and make decisions on the images. And you will also understand how you can implement computer vision in your business case. But at OCCO, we actually help architects to find and source furniture. And as a part of that, we get a lot of images of furniture. And we then have to analyze them somehow and make recommendations based on them. And we use computer vision in 3 ways. So first, we help to categorize products. Then we make recommendations, and we also allow them to search visually. But why should you be interested in computer vision? Well, computer vision is actually used in pretty much every industry in some way or form. And most popular ways to use it are probably content moderation, quality assurance, security, or verification. And often we get repetitive tasks with images that we want to automate. And we can automate them if we can ask like a concrete question and develop an algorithm to answer that question. And in computer vision, in machine learning, we have a couple of frequent questions that we come across. So for example, what is in the image? And we solve that with image classification. We also ask, where is an object in the image? And we solve that with object detection. And sometimes we ask, do these 2 images contain the same? Very common in verification services. And we do that with image similarity. And in OCCO's case, we often ask the question, what similar images do we have in our database that we can offer to the user? And we do that with image retrieval. But before I get to how a computer understands images, let's ask how we as humans understand what's in the picture. So you probably have never described a bed in your life, because you have you understand the abstract concept of bed in your brain. You have seen a lot of brains in your life. You have seen a lot of beds in your lifetime, and you have come up with this concept. But if we did, we would probably start with saying that it has this flowier contours on the top, and more straight horizontal ones at the bottom. It has kind of rectangular shapes on the top left corner. And as we'll see, a computer actually kind of learns in a similar way to understand patterns to build up bigger concepts. But how do we actually get the images? So we get the images from light reflecting from objects. And this light is captured with camera. And camera turns the light into pixels. And this is the format we all know, the JPEGs, PNGs. But the problem is, it's just too many pixels, too many dimensions. We would have to write millions of rules to even make a simple algorithm to decide if something is a bed or a chair. We'll see how we'll solve that. The other problem is context. So it's never enough to look at just 1 pixel. We always have to consider many pixels in the vicinity. And then we have to consider the larger vicinity, and then we have to consider the actual whole picture usually, if we can make some decisions. Okay, this is a bit broken slide. Doesn't matter. So what you might have learned in school are matrix multiplications. So these are basically actions when you take a grid of numbers and you multiply it with another grid of numbers. And in computer vision, we call that a convolution. So what we simply do is we have some kind of grid, we move it over the image and multiply all the pixels with this grid. Then we sum up the output of the grid and we replace it in the output, replace the original pixel with the output. What basically happens is, it emphasizes some features. So for example, you can have an edge detection convolution, and as you see on the image, it emphasizes the edges. So already this simple action helps us to learn about the complexity in the image. So this is how the convolution action works. You take what's called a kernel, 3 by 3 grid of pixels. Can be 5 by 5 or 7 by 7, but 3 by 3 is most common in computer vision. And you move it over the original picture, and you replace the output. But then, how do we get all these convolutions? We said there's going to be millions of rules. It would be really hard to come up with hundreds of thousands of different kernels. So what do we have that can kind of learn on its own? It's machine learning. So we show the algorithm something, we calculate the loss or the difference, and then we teach the network. So, for example, we have a data set of beds. We start running the convolution on the initial image. We get the output. And initially, the calculations are randomized. The kernel is randomized. We get the initial output. We downsize it. We run the convolution again. And we do that in layers. So we kind of have like a layered multiplication that's initially completely random. What we then do is we compare the output with our data sets, our loss function, and we calculate the difference. And then, step by step, in small optimizations, we optimize the neural network to basically start giving us what we want. And what we end up in the last layer is embeddings. So embeddings are just a smaller representation of everything that's in the image. They're just a list of numbers, can be from 2 to many thousands. What we have found is we can describe images for our use case in just 256 numbers. So what we have really done is we have taken an image that contains millions of pixels, and we have kind of compressed it into a much more meaningful representation. So we can say in just kind of describe in 256 numbers what's in the image. But to make it easier to understand for you, let's consider just two-dimensional embeddings. So in that case, we would take the original image, the bed, and find a way to describe it in just two coordinates, x and y. What would then happen if our network is trained correctly is that other beds would be really close to that vector as well. And we calculate the closeness based on the angle of the vector. And the angle distance is called cosine similarity. It's a bit different from Euclidean, what we're usually used to. So if you're interested in defining vector similarity, look up cosine similarity. What we would also expect is anything that's different has a different embedding. So it has a huge angle between the other things. So what can we do if we have this kind of description of the object in a embedding form? Well, we can make classification to answer what's in the image, give it a category. We can also compare to say if the two images contain the same thing, and we do that with the same cosine similarity. And we can search for similar ones. So if we have like a search functionality in our product, we want to find all similar things that have similar embeddings. And by the way, this is not just for images. You can use the same methodology for text as well. So you can turn a sentence into an embedding, or even a whole document. And then you can find the closest similarity and use it as a way to search. But at OCCO, we took a part of our database, 60,000 products, and we turned them all into embeddings. So this is what you see. Similar things cluster nicely together in specific clusters. And what you actually also see is that things that are not exactly the same category, but kind of similar, like for example dining chair and the office chair, also have their clusters placed together. What can we do with this? Well, we can take our original image. We also turned that into embedding format, and we asked like what is in the image. And for that, we just place it on this graph. And okay, we say if it falls in bed's cluster, it must be a bed, right? Another thing we ask is what similar things we already have in our database. And for that, we just take the closest neighbors. Actually, taking the closest neighbors is not trivial. So you can, of course, do like a for loop, run over all of the products. Would take you a couple of hours, which is not suitable for the user. And for that, there's a lot of algorithms for approximate nearest neighbor. So if you're interested in similarity search, look for approximate nearest neighbor. And extremely interesting use case, in my opinion, is what can we do if we train like a reverse network that takes the image, that takes the embedding and reverses it back to an image. And if we had this kind of network, what would happen if we take like embedding from some intermediate space where there is no furniture yet? Well, what we would get is actually generative design. The algorithm would itself come up with the pixels, the image. And of course, this would be excellent for mood boards to make designers, to give them inspiration. It's also interesting what would happen if we took like a network that turned images into embeddings and outputted, if we took one network that turned images into embeddings and another network that turned words into embeddings, and then we used the network that turns words into embeddings to back generate the images. So we could just write what do we want to see. And I think this is going to be extremely influential in next 4 to 5 years, and hugely make designers' life much more interesting, much more convenient, because they don't have to spend hours of just drawing up stuff. They can just think, they can do their creative work. And now some practical lessons we have learned when we have been building our computer vision systems. So, of course, we started with a really nice data set, and we trained a classifier. And the classifier worked really well. Gives us the exact category of new products coming in. But what happens if we try to use the same model to give recommendations or search results to users? Well, what happens if a user can submit their own pictures? Of course, they're not going to submit nice pictures with white backgrounds. They're going to submit pictures like this. Something that has completely different angle, completely different color, completely different lighting. So we had to go back and go and collect a similar data set of what the people were actually putting into our database. And then we trained a new model that understood that no matter whether it has a white background or this kind of real background, the embedding should be the same. And then we can give accurate recommendations even if the user's pictures and our pictures are completely different.